In this unit, we're going to be looking at time response. And so in the textbook, we've skipped over chapter 3 and we're moving on to chapter 4. And so what we're going to be looking at in this unit is we're going to be focusing on the analysis of the system transient response. So before we look at examples of actual systems, we're going to talk about some terminology and some key things that we need to know first. So first of all, we can recall that our total response is really the sum of our natural response and our forced response. So total response is equal to our natural response plus our forced response. And so one thing to note here is that nowhere in that representation is there a transient response. So this is sort of a terminology thing, but it turns out that our transient response is this total response when our natural response is large. So transient response is when our natural response is large. And then in contrast to that, we have steady state response. And so these are items that we talked about a little bit in our introductory videos. So our steady state response, conversely, is when our natural response is small. And so the example that we looked at in previous videos was we talked about an elevator, and we said, well, if we have the position of the elevator, so if we have the floor, let's say our elevator is initially here at this level, and at some time we give it an input to go up to a different level. So our input signal would look something like this. So it instantly is told to go here, but of course our elevator isn't going to just magically jump from one floor to the other, so it takes some time to do that. So we end up with something like that. And so essentially what we're looking at then is this region here is our transient response. Let me do that in a different color because it's not the whole red curve, but rather just that region, which is our transient response. And then once it's not changing values anymore, that's our steady state response. So there's a little bit more detail on that on a footnote on page 10 of the textbook, sort of describing the difference between all of that notation. And we'll talk about this in later videos, but our natural response is, the form of that is due to the system itself. So that would be like our elevator and any components that are affecting how that system responds, whereas our forced response is going to be based more on the input. Okay, so now that we have a better grasp on that notation, let's go back to sort of our transfer function, and let's talk about the general form, and we're going to talk about a couple key things and terms that we need to know before we can get into more details with our time response. So we're going to look at the general form of transfer functions. And so we're actually going to look at two. The first one I'm going to put up here is one that we've already seen. And so this one is our ratio of polynomials. And so with our ratio of polynomials, we said we had some coefficients in the numerator, b sub m minus 1, all the way down to b naught, that are multiplied by s to the m minus 1, all the way down to s to the 0, respectively. And then in our denominator, we have a similar polynomial with a to the n minus 1, all the way down to a naught, multiplied by s to the n minus 1, and s to the 0, respectively. So this is our general form that we've seen before, but often we're going to need a different general form that's going to be a little more useful to us, and that's our factored form. So in our factored form, we have s minus z1 times s minus z2 all the way down to s minus zm in the numerator. In the denominator, we have s minus p1 times s minus p2 all the way down to s minus pn. And so again, this is called our factored form. So why have I used the nomenclature or the parameters z and p? Well, the reason is that our z is representing zeros and our p's are representing poles. So our z1, z2, all the way down to Zm are what we're going to call zeros of our transfer function, g of s. And so this nomenclature is very important. We're going to be using that throughout the rest of the semester. The reason that we call these values 0 is, of course, if we let our s equal to one of those. So when s equals any one of those z's, so we'll just keep it general and say z sub I, then what happens is our transfer function is equal to 0. So that's why we call those values zeros. Similarly, we have poles p1, p2, all the way to p sub n. So these are the poles of g of s. And so again, that's important terminology there. And so with our poles, whenever s is equal to a pole value, so when s is equal to p sub I, we have that our transfer function is something divided by 0, so that means our transfer function is infinite. So a couple other things to note about the two forms. We don't show any constants, but either of these two forms here can be multiplied by a constant value, so we might have some gain k multiplied here, so we can do that for either of our two forms. One other thing too is in some cases we might have a pole and 0 at the same location that can be canceled out, but we leave them for some reason. And so we'll come back to that a little bit later. Right now we just want to get familiar with this terminology of our poles and zeros, because again, that's going to be very important as we go through the rest of the semester.